So let's take a walk through the citric acid cycle. So the citric acid cycle, unlike glycolysis, is a cyclic pathway. So we're going to have some interesting things to think about when it comes to how we think about regulation of this pathway, because there's not really a first or a last step in terms of a circle. There will be in terms of how we learn about it. But we're going to kind of take an overview of the chemistry that happens here, and then I'll zoom in on our figure on the right here and take a deep dive as to what is happening on each step. Okay, so first I sort of want to orient you and have you think about the citric acid cycle kind of like a clock. It's going to be a little bit of a not exactly symmetrical clock here, but I want you to think about it in terms of kind of a left half and a right half of our clock here. Okay, and we're going to call this stage 1 and stage 2. Okay, I'm going to get to the net equation here in just a minute, but I want to sort of talk big picture about these different stages. I want to highlight first, too, that we're going to talk about pyruvate dehydrogenase a little bit here and then a much more detailed look on another video. But pyruvate dehydrogenase chemistry often is called step 0 of the citric acid cycle, because when you consider it from the standpoint of carbohydrate or glucose metabolism, you have to take pyruvate first and make it into acetyl-CoA. All other fuels can be made into acetyl-CoA, and so that is sort of the entry point for the citric acid cycle. So if we think about sort of these two halves of our cycle here, I want you to think about some terminology that we used when we talked about enzyme active site, right? I want you to think about stage 1 sort of being like chemistry on the substrate. And so what we're going to see sort of in this first half of our process is we're basically going to see carbon dioxide production with energy generation. Okay? And so we're going to see carbon dioxide production with energy generation. And I'm going to get to some of the details of how this happens when I do our walkthrough, but highlighting that we're going to see energy in the form of NADH and then GTP. And then obviously CO2, we know what CO2 is, but we're going to see CO2 production from decarboxylation of both alpha and beta keto acids. So we're going to see decarboxylation of alpha and beta keto acids. And just to give a preview here of where we're going to see these different things, alpha keto acids, okay, are going to be pyruvate, okay, and then alpha ketoglutarate. So we're going to revisit those in a minute. And then beta keto acid is going to be isocitrate. And as we'll see in a minute, isocitrate is not a beta keto acid, but we are one redox step away from making it into a beta keto acid. So that's sort of stage 1. So what we're going to see over in these 5 steps here is we are going to see the production of CO2 and the production of energy as NADH and GTP. So remember when we did our enzyme active site chemistry, we said chemistry on the substrate, use all reagents, return the enzyme to active site to sort of its beginning stage. So we're going to use sort of that same terminology here, and we're going to define stage 2 as regeneration of the active state. So regeneration of the active state. And notice I didn't say active site here because we're not talking about one enzyme. We're actually going to have 3 enzymes that we're going to address here in this second stage, okay? And what we're really going to be talking about is the regeneration of oxaloacetate, a really important branch point metabolite, but in this case, it's important for kind of finishing out the citric acid cycle. So we start stage 2 with the molecule succinate. And I'm going to remind you that succinate has functional groups that suck, okay? And that's because what we have here is we have 2 methylene groups. We essentially have an alkane. I'm going to zoom in here so that I can write a little bit better. And again, giving you this 30,000 foot view right now so that when we go through sort of and walk through the details here, it'll make sense. Ultimately, we have to take succinate and we need to convert it into oxaloacetate. Right, that's our OAA. And here's the chemistry that's going to happen. We're going to convert this alkane into an alkene. And then this alkene to an alcohol. And then that alcohol to a ketone. Okay? And so the chemistry that's going to happen to do alkane to alkene, alkene to alcohol, and then alcohol to ketone, okay, that's going to be oxidation, hydration, oxidation. And that's going to be some chemistries that we're going to see a lot. All right, so before we dive into the details of this cyclic pathway, let's remind ourselves what the overall sort of chemistry is. And this is a long equation, so I'm going to have it kind of written as reactants on top, substrates on top, products on the bottom. And again, allowing us to connect substrates that become products is a nice way to remember sort of the chemistry that happens. So we've got acetyl-CoA plus 3 NAD pluses plus FAD plus GDP and PI plus 2 waters. And that's a lot to remember, but if you connect it to the pieces that we make as products, it will make a lot more sense. So acetyl-CoA, those 2 carbon atoms that are on that acetyl group ultimately become 2 carbon dioxides. The NAD pluses, as they become NADHs, as they grab those electrons. FAD becoming FADH2. GDP and PI together becoming our GTP. Okay. And water actually gets used up sort of in that chemistry, so we're not going to see sort of water connected to anything. But that's our overall sort of equation for what happens. So let's take a deep dive now. It's going to take a little bit of time here, but we're going to walk through these structures, and hopefully it'll be a good storyboard to help you remember everything that happens in the citric acid cycle. Okay, we're going to start really with what we've identified as sort of that step 0, pyruvate. So pyruvate being the endpoint of glycolysis, pyruvate is an alpha keto acid. So remember, we're going to have 3 decarboxylation steps we'll see here. Alpha keto acids are going to be pyruvate and alpha ketoglutarate, and then we'll have a beta keto acid sort of as hidden in our isocitrates. We're going to see that in just a minute. We'll have another video to go through the detailed chemistry for pyruvate dehydrogenase. The chemistry is ultimately going to take this acetyl group and it's going to put it on CoA. And I love that when they write CoA as CoA-SH because that reminds us that there's that important reactive thiol group. So we generate this thioester. So here again is this acetyl group from here that it got attached onto CoA to make our CoA, our acetyl-CoA. And then we have the other CO2 group come off as carbon dioxide, and this was an oxidation step. So we have the concomitant reduction of NAD plus to NADH. So we're going to take a deep dive on this enzyme because I want you to think about this enzyme, pyruvate dehydrogenase, and we'll also see it for alpha ketoglutarate dehydrogenase, that these enzymes are like this giant mall, if you will. We talk about stores, right, where there's like two stores that we have. We've talked about a couple of bifunctional enzymes. This is a multi-enzyme complex. So there's 3 basic stores that live in this complex, but there's lots of copies of each of those stores. So we're going to talk about E1, E2, and E3 as the different stores. So we're going to have another video that will go through the details of that. Okay, but ultimately we get to acetyl-CoA, which is the starting point for the citric acid cycle, reminding ourselves that you can have ketogenic amino acids that can be converted into acetyl-CoA. You can also have the breakdown of fatty acids into acetyl-CoA. But wherever you start, acetyl-CoA in step 1 is going to be combined with oxaloacetate using the enzyme citrate synthase, and you're going to make the 6-carbon molecule citrate. So we're going to have sort of some words that we'll use to sort of think about the chemistries that happen here. So this is really carbon loading. So carbon loading. And we're so small here, zoomed in here. My pen is super fat there. Okay, citrate synthase is really carbon loading. We're going to be taking a 4-carbon oxaloacetate, combining it with a 2-carbon acetyl-CoA. We're going to assemble those guys together here to generate citrate, and then we're going to liberate free CoA. So that's the carbon loading step, okay? Now we've got citrate. Now one of the things we're going to highlight here is in the next step, after the one that we're doing right now, we are going to be decarboxylating a beta-keto acid. We do not have a beta-keto acid here. And right now what we have is we have a tertiary alcohol. We cannot oxidize tertiary alcohols. So what we need to do is we are actually going to move this OH group over here. Historical name for an enzyme, so unfortunately it doesn't have anything to do with the kind of chemistry that's happening. It's called a conatase. But we are going to move this guy over here, and we generate an isomer of citrate called isocitrate. No other pieces that we need for that enzyme to do its chemistry. So a conatase interconverts citrate and isocitrate. Now, we highlighted this guy as a beta-keto acid. And you're like, I don't see that as a beta-keto acid. It's a hidden or a disguised beta-keto acid. Because what we're going to do in the next step is let me label these. So that was carbon loading, and then we did rearranging. Okay, so we made citrate into isocitrate, and now we are going to have oxidative decarboxylation. So that's our isocitrate. So this is our isocitrate dehydrogenase. So oxidative decarboxylation. Okay, and this again is going to be a beta-keto acid. So I'm going to walk through kind of what happens here. We're going to oxidize this OH group and make it into a ketone. And now we've got a beta-keto acid. So this is the CO2 that's going to come off. So we've got beta to that, a keto group. Beta-keto acids decarboxylate on their own. We don't need additional cofactors. So oxidative decarboxylation is going to remove this CO2 group. And so you'll see that this is what we're going to have left here. Okay, that is alpha-ketoglutarate. So alpha-ketoglutarate now, just like pyruvate was, it is a alpha-keto acid, okay? So now we're going to have another decarboxylation step. So decarboxylation. But now this is of an alpha-keto acid, okay? I'm just going to remind us up here that this was a beta-keto acid. So alpha-ketoglutarate, because it's like pyruvate, we are going to have this the same sort of multi-enzyme complex kind of involved in what's doing chemistry. So that store that has E1, E2, E3, there is a version of it that will use alpha-ketoglutarate as a substrate. Same kind of chemistry. I didn't mention this when we were talking about pyruvate pyruvate dehydrogenase, is we need to have vitamin B1 for that, TPP. Anytime you're doing decarboxylation of an alpha-keto acid, you need to have vitamin B1, TPP, as part of that, okay? Same kind of chemistry, though, because we're going to have CoA come in, okay? We're going to take and we're going to transfer essentially this group, okay? I should say this group right here. Not an acetyl group, not a 2-carbon group. It's going to be a 4-carbon group, gets transferred to CoA, and that's going to make succinyl-CoA, okay? And so this is the CO2 group that's coming off there. Okay, you can see these are labeled here, so we can sort of follow the carbon label, if you will. And then because this is a process that requires oxidation, we have the reduction of NAD plus to NADH. The end of this chemistry is succinyl-CoA. So again, let me move this just so that we can sort of see. I'm not going to be able to move it easily. I was going to move this guy sort of over here to say that that's the chemistry that's happening there, is alpha-keto acid decarboxylation. And then the last step that I'm considering as part of stage 1, so this is a little lopsided, it's really 5-step, 3-step, is we do this chemistry that takes this high energy succinyl-CoA. Remember, a thioester bond is high energy. So we're going to be able to use that in a substrate level phosphorylation type chemistry. okay, to synthesize GTP. Notice it's not ATP, it's chemically equivalent GTP, and we're left with succinate. Okay, so I'm going to zoom out here for a second just to do a high-level recap of everything that we just talked about with sort of stage 1 here. So stage 1, 5 steps I want you to think about. We do carbon loading by combining oxaloacetate and acetyl-CoA to get citrate. We need to do a little rearranging to get it into the isocitrate form, which has that secondary alcohol that then we can then oxidize. Third step is isocitrate dehydrogenase. This allows us to do decarboxylation of a beta-keto acid, but we first have to generate that beta-keto acid by oxidizing that alcohol to our ketone. We generate that beta-keto acid. That's an intermediate in this process, not really isolatable. And then isocitrate will oxidatively decarboxylate to generate alpha-ketoglutarate. Now we have an alpha-keto acid that we can do decarboxylation using that multi-enzyme complex that is alpha-ketoglutarate dehydrogenase. Then we're going to be left with that 4-carbon piece left on a CoA, which is succinyl-CoA. And the last step is doing what equates to substrate level phosphorylation, taking that high-energy thioester bond and using it to synthesize GTP from GDP and PI. And at the end here of this first stage, we are left with succinate. I know, a lot. This is the only other metabolic pathway we're going to go through in such detail. We go through glycolysis like this and the citric acid cycle like this. Okay, so now let's talk about what we need to do here. Let me flip back over here. Remember, we were talking about stage 2 is really the conversion of succinate to oxaloacetate. So we're going to have an alkene that we oxidize, an alkane that we oxidize to an alkene that we hydrate to an alcohol, and an alcohol that we oxidize to a ketone. Okay, so let's take a look at what we have here. Let's sort of zoom in here, and I'm going to highlight and draw some unique pieces to some things that are happening here. So again, starting with succinate here, we're going to do, and let's highlight and remind ourselves that when we're talking about this chemistry, so let's highlight this here. When we're talking about like this group right here, that is referring to these carbon atoms. I don't know how they showed up right there, but those carbon atoms, these guys right here. So we've got an alkane that we oxidize to an alkene, and then an alkene that we hydrate to an alcohol, then an alcohol that we oxidize to a ketone. So that's those 3 steps, but let's kind of talk about the details, anything that's unique that we have here. Okay, so highlighting what happens with succinate dehydrogenase, this is oxidation. And I'm going to highlight that when we do this alkane-alkene type oxidation, this is going to be a time where we often see FADH2. I should say it's really FAD. Okay, and succinate dehydrogenase, we're going to see this guy again. This is actually complex 2 in the electron transport chain. So we're going to see that in our next learning unit here. Okay, oxidation of alkene to an alkene takes succinate and converts it to fumarate. That enzyme for doing that is succinate dehydrogenase. I don't think I mentioned this enzyme name from our last step when we do that substrate level phosphorylation. That's really succinyl-CoA synthetase. And it's a weird one. You sort of want to say synthase because we've seen those before. Nope, synthetase. So it's succinyl-CoA synthetase. Okay, then succinate to fumarate is by succinate dehydrogenase. And then we have the enzyme fumarase. So that's going to be the one that hydrates our alkene to make our alcohol. You don't really need to know the details of this, but remember, enzymes can do things stereospecifically. So notice that this is a transalkene that we have here. And we have stereospecific and regiospecific addition of that OH group to a specific carbon in a stereospecific way, and we generate L-malate. I just need you to know that it's malate. And then the last step is malate dehydrogenase is going to oxidize this alcohol to a ketone, generating oxaloacetate, regenerating sort of our metabolite that we need to continue this cycle. So a couple of other important pieces to highlight, and we've talked about many of these in lab already. Malate dehydrogenase has a large positive delta G. So a couple of things to highlight what that means. We have very low concentrations of oxaloacetate. That's okay. We just need a little bit to kind of go through citrate synthase, which actually has a large negative delta G. So it's able to pull those reactions forward. So these reactions are really coupled, citrate synthase and malate dehydrogenase. You guys know that has a lot to do with the research that we do in the laboratory. So another thing to point out, and you'll sort of note this as we go through, a lot of times when we see NAD plus and NADH sort of interconversions, what we're going to see is that we are doing alcohol and ketone sort of redox chemistry. Remember, FAD, we see a lot of alkane-alkene sort of chemistry. So that's sort of a theme that we're going to tend to see here. But again, getting back to oxaloacetate, it doesn't matter if we just have a tiny little bit of it. We're going to consider oxaloacetate to be a catalyst in this process, something that you use in small amounts, helps the reaction go faster, and at the end is regenerated. So that's consistent with sort of the definition of a catalyst, and so oxaloacetate can be thought of as a catalyst for the citric acid cycle. Wow, I know that was a longer slide, but a lot to kind of have us run through and do a walkthrough of the citric acid cycle.